All right, good morning, everyone. I'm happy to introduce Laura Kreidberg, who is giving our seminar today. Laura did her undergrad at Yale, then she did her PhD at the University of Chicago. She was a postdoc at Harvard for several years, and since 2 years ago, she is one of the directors of Max Planck Institute at Heidelberg. Thank you, Marie.
Wait, you have to unmute.
Okay, I'm unmuting. Okay. Can folks online hear me okay?
Yes.
Yes. Okay, good. Well, it's such a pleasure to be here. I know it's a little bit weird timing. This ended up being the only week that I could come. So I'm happy to see you here, and I hope I haven't interrupted the long weekend too much. So today I'm going to be talking about exoplanets and really what they are like. So I think more than any other astronomical object, planets are really places. We can relate to them since we live on a planet ourselves. So this is familiar probably to a lot of you, but just to wake everybody up, here's my brief history of extrasolar planets. Just a little less than 30 years ago, the first planet orbiting another star was detected. That was the hot Jupiter 51 Pegasi b. And if you fast forward to today, we now have over 5,000 confirmed extrasolar planets. This is a milestone that we reached just in the last couple of weeks, I think, very recently. And I'm showing this figure on the right-hand side of the slide, showing the number of planets discovered every year. You can see the huge growth rate in planet discovery, and I think that will continue with ongoing surveys like TESS and KOPS, and also future missions like Plato. Okay, so if you break this down into some statistical information, we know that planets actually outnumber stars in the galaxy. So sun-like stars host at least 0.7 planets on average, and M-dwarf stars, smaller stars, are even more common than sun-like stars. They're the most abundant type of star in the galaxy, and they host even more planets, so at least 2.5 planets per star on average. And these are lower limits because we haven't yet had the sensitivity to explore for smaller planets or longer orbital periods. So point is, there are lots of planets. And the importance and excitement of this discovery was recognized, of course, with the Nobel Prize awarded to Didier Queloz and Michel Mayor in 2019. Okay. So already we have learned that exoplanets are much more diverse than the solar system. This is a very typical kind of plot showing planet mass versus distance from the host star. This is now really old, but it still highlights a couple of interesting populations of planets that I'll talk about today. So one of these is very hot planets on short orbital periods. The shortest orbital period for any planet known is less than 12 hours, maybe even less than 6 hours. I can't remember. But when you heat up a planet, it makes it easier to study, and it helps you learn about what's inside. So I think particularly for gas giants, the volatiles in their atmospheres are heated up in the gas phase, which makes it very easy to see things like water and carbon monoxide, carbon dioxide, so that you can learn about the building blocks that the planets were formed from. There's also an important population of planets that we don't have any analog for in the solar system. So these are intermediate in size between the Earth and Neptune. And there's a lot of ongoing discussion and debate about what these things are. Some people say they're super Earths, some people say they're mini Neptunes. Maybe there's something else entirely. My preferred name for these planets is Neptini, because I think, we really don't know what exactly they are. And so I think it's fair to give them a new name. There are also planets on the boundary between what we would typically consider a star versus a planet. This allows us to probe the upper edge of planet formation, or maybe the lower boundary of star formation, as well as a whole bunch of very weird things. So highly eccentric planets, planets orbiting white dwarfs, planets orbiting two stars, and the list goes on. And all of this is to say there's a big part of parameter space that we haven't been able to see yet, including most of the parameter space where the solar system planets lie. Okay, so given that we have found all of these planets, we have an idea of their demographics, what the census of nearby planets looks like, now is a very exciting time to go and characterize the planets in more detail. And in my work, I focus on the atmospheric composition of the planets and their climates, to learn both how the planets form, how they evolve over time, what they are like, so how the atmospheres are shaped by the very extreme environments some of the planets are found in, very close to their host stars, tidally locked. And of course, ultimately, a very big question that motivates me, and I think many others in this field, is whether we can infer the existence of life on another planet by looking at its atmosphere. So just a few very brief words on how atmosphere characterization works. I think ultimately the long future of the field is to go more in the direction of direct imaging, where you can spatially separate the planet from the star and just take a picture, get a spectrum of the planet directly. But that's really challenging. And one of the intermediate steps we can take for very special planets that are transiting their host stars is to observe a planet either during a primary transit when it passes in front of the star. And in that geometry, the starlight filters through the planet's atmosphere where it can be absorbed or scattered by atoms or molecules, clouds or haze particles. And so the idea is that at wavelengths where the atmosphere is more opaque, more of the starlight is blocked. And so the planet appears a little bit larger. And conversely, when the planet passes behind the star, any thermal emission or reflected light from the planet is blocked by the star. And so by combining these two techniques, it's possible to measure the chemical composition of the atmosphere, the temperature, the climate, and also the presence of clouds or haze. Okay, so this is a nice cartoon. I want to show some pictures of what this really looks like in practice that are closer to home. So this is what the Earth looks like from space. This is an image of the Earth, I think, taken from the International Space Station. You can see the moon in the background. And what I want to draw your attention to is the blue Rayleigh scattering signature from Earth's atmosphere. I don't know if you can see. No cursor, that's okay. But you know what I'm talking about. This is why the sky is blue. That's why you get that fuzzy blue edge where Earth's atmosphere is. If you move to the infrared, that Rayleigh scattering signature is gone. And so you can see that the Earth looks a little bit smaller at 8.6 microns than it does at optical wavelengths. So if I toggle back and forth, you can see that layer is lost. If you move just 1 micron redder, you get the ozone band. And again, Earth is a little bit bigger. So I'll go back and forth here. So here's out of the ozone band. Here, ozone is strongly absorbing. And so you can see that the atmosphere is slightly thicker at 9.6 microns than it is at 8.6. Now, this looks super easy if you can just like take a picture of your planet from right next to it. In practice, this is extremely difficult. So I always have to show at least one slide with real data because I think it would not be very honest to only show a cartoon, only show these beautiful pictures. This is real Spitzer observations of a hot Jupiter. The top panel is showing the raw time series, so brightness over time, over a complete orbital revolution of the planet. You can see all kinds of wiggly stuff. In the middle, there's a big dip. You can probably tell that's the transit. But the most important thing about this plot is the scale. So I noted on the y-axis with a red arrow, 1%. So you're seeing about 1% variation in brightness due primarily to instrumental effects. So the temperature of the spacecraft is changing. The pointing of the telescope is also variable. And if the light from your star falls on slightly different pixels that may have slightly different sensitivity, you can get this kind of chopping. That's what those really short frequency wiggly things are. But with very careful work, a lot of time, a lot of hours of grad students' lives, including my own, it's possible to correct for these instrumental effects and identify signals that are at least an order of magnitude smaller than the instrument noise. And so the bottom panel is showing the phase curve, one of the first ever measured phase curves for a hot Jupiter. And you can see as the planet is going behind the star, it's a secondary eclipse, the light from the planet is blocked. The hot day side rotates out of view. So you get this sinusoidal modulation in the brightness. The transit is off the bottom of the plot. And then you have the hot day side rotating back into view, and the planet is eclipsed again by the star. So this is pretty spectacular. I mean, this is one of the first times we were able to study the climate of a planet outside of the solar system. It's also one of the very easiest cases. So this is one of the brightest hot Jupiters. There's a reason we did this one first. It's the most observationally accessible. If we want to push this to smaller planets, cooler planets, planets more like Earth, we have to push down to at least 1 or 2 orders of magnitude more precise of a measurement. So observationally very challenging. Exoplanet atmospheres are also challenging from the modeling perspective. And I like to show this picture of Jupiter taken with JunoCam to illustrate, this atmosphere is clearly not one-dimensional. It is not cloud-free. You get these beautiful vortices. You get different kinds of clouds and hazes forming. And so from a modeling perspective, we care about what's happening in the atmosphere, both on small distance scales, so microphysical cloud and haze formation, to planet-wide distances. So how is atmospheric circulation affecting the temperature distribution from the day side to the night side? And also how the atmosphere changes over time. So everything from short time scales, that's weather, to atmospheric evolution over billions of years. So how much atmosphere can you lose over that time, for example? So both observationally and theoretically, I think exoplanet atmospheres are going to keep us in business for a long time. There's a lot of work to do. And I want to just briefly introduce my own department that I'm building at MPIA. This is what we look like at the moment. It's growing very quickly, so this slide is going to be out of date pretty soon. But the goal is to have a critical mass of both observers and theorists and also instrument builders together all in the same place so that we can really tackle this problem together. Okay, good. Any questions before I move on to the rest of the talk? No, okay. So what I'm going to do for the remaining half hour or so is walk through a couple of different frontiers in exoplanet atmosphere characterization that are really hot areas right now. And I'll kind of work down in size of planet from gas giant all the way down to Earth-sized planets. And the first of these is using the atmospheric composition of gas giants as a fossil record of how the planets formed. I know there's a lot of interest in this department about how this works. So the basic picture is that planets form in disks, gas giants accrete a primordial atmosphere from the protoplanetary disk. And the composition of that atmosphere is very sensitive to the conditions in the disk where the planet formed. And the figure that I'm showing in this slide, it's a very classic figure from Kreidberg showing the carbon to oxygen ratio for gas, that's the black line, and solids, that's the dashed line, as a function of distance from the star. And what you're seeing here is that as you move away from the star, you have different volatile species freezing out. So for example, at a couple of AU, you get the water ice line, so the water freezes out from gas phase to solid phase. And depending on how much gas versus solids your planet is accreting, you can end up with very different atmospheric compositions, ratios and abundances of carbon and oxygen. So in the end, the composition of the atmosphere is sensitive to the formation location, the ratio of gases to solids that are accreted, when in the lifetime of the disk the planet formed. So this is one static picture, but the disk composition is evolving over time. That's a modeling puzzle. So I'll leave that aside for the time being and focus on how well we can actually measure the compositions of the planet atmospheres today. And we have some grounding in the solar system. So like the very, very simplest picture of the solar system is that there's a trend in atmospheric metallicity with planet mass. So Uranus and Neptune are thought to have much more metal-rich compositions, about a factor of 100 enhanced metallicity over solar composition. Saturn falls somewhere in the realm of 10 times enriched over solar, and Jupiter is a couple of times. And so a question arises, why is this trend there? Is it a universal outcome of planet formation? Do we expect this for exoplanets as well? And so my job as an observer is to go actually study the exoplanets and see if we can get any new data points on this plot, because no matter how well we measure these quantities for solar system planets, there's only 4 giant planets to work with. Okay. So jumping right into it, this is one of my most favorite examples. It's a hot Jupiter called WASP-43b that we targeted with very intensive observations with the Hubble Space Telescope. A lot of the best data for exoplanets are coming from space-based facilities simply because the Earth's atmosphere is in the way from the ground. And so it makes it very challenging to detect chemical species like water that are also present in our own atmosphere. So these are spectra of the planet measured with the Wide Field Camera 3 instrument, which operates in the near infrared, focused right on an absorption band from water that I've marked on the plot. And you can see that both for the thermal emission spectrum and the transmission spectrum of the planet, we get very strong absorption features from water. We were able to retrieve the water abundance by doing atmospheric retrieval is essentially just running a whole bunch of one-dimensional models with varying abundances of water, varying cloud properties, varying temperature pressure profiles. And what we found at the end is that the water volume mixing ratio in the atmosphere has to be between about 200 and 3000 ppm. Okay, so if I show this to the cosmologists, they're like wildly unimpressed because they think, okay, you've measured this thing to an order of magnitude, good for you, like they're aiming for 1% precision cosmology. But the most relevant takeaway is that this measurement precision allowed us to put an exoplanet on the solar system plot for the first time. It's a proof of concept that you can actually measure these precise water abundances for exoplanets. I should say as an aside, it is amazing to just see the water in the atmosphere of a gas giant. We can't see it for the solar system planets because they're so cold that the water has condensed out of the easily observable parts of the atmospheres. And so there's a huge amount of effort going into estimating the water abundances for Jupiter in particular. But even with like the Juno mission, which was designed in part to measure the water abundance, we still don't know it very well, factor of, something like 5 uncertainty. And so it's really, really incredible to look at an exoplanet and then bam, there's the water. Yes?
I have a question over the last plot.
This one?
Is why are the gas giants why ice giants are coming after gas giants? Like, shouldn't be gas giants, water, and then ice giants?
Like, is the question, why is the trend this direction? That's a great question. I mean, there are multiple explanations for why. I think that one possibility is that if you form your planet by pebble accretion, you can reach a pebble isolation mass where you stop accreting these, rocky, icy little things, and you start having runaway accretion of gas, which is drier. And so that naturally gives you a less volatile, more volatile pore composition for a Jupiter-sized planet than for a Neptune-sized planet. Yeah. Okay. Good. So we measured our water abundance for WASP-43b. We put it on the plot compared to the solar system. Looks like the trend holds up pretty well. So we were feeling pretty good about ourselves after this measurement. We were like, all right, maybe this, even though this exoplanet is in an extremely different environment than Jupiter is, it has like a less than 2-day orbit compared to many years for Jupiter. Maybe it has similar formation history. Great. So if you fast forward to today, we see that exoplanets, as usual, are much more complicated than they first appear. They're more diverse than the solar system. And so the figure on the right is an updated plot from Luis Wellbanks, where he took the water abundance measurements and also abundances of alkali metals for a sample of something like, I don't know, order of magnitude 10 hot Jupiters that have been studied over the last decade or so. And he found a couple of really interesting trends, in particular, one showing that many of these planets appear to be water depleted relative to solar composition, but not depleted in refractories. So not depleted in sodium, not depleted in potassium. And so that, there's a lot of scatter here. I want to show a couple of data sets just to convince you that some of these low water abundances really do hold up for very, very careful analysis. Here's an example of a hot Saturn, Kelt 11b. This is a Hubble Wide Field Camera 3 transmission spectrum of the planet. And we looked at this data set and we found that the shape of the water feature is kind of strange. It, where is my old-fashioned pointer? Yes, okay. So the shape of the water feature is very weird. It's sort of, you get this characteristic bump at 1.4 microns, and then it kind of flattens out here. It's in contrast to a solar composition gas where you would expect the transit depth to decrease again, something more like this green line here. And we needed some extra opacity to fill in this bump to explain the larger transit radius at these longer wavelengths. And no matter what we did with our models, we found that we needed collisionally induced absorption, CIA, from H2 to reproduce this shape, which means that we're seeing all the way down to the hydrogen continuum, super deep in the atmosphere, which is only possible for a very metal poor composition. The more metals you put in, the higher altitude you're probing. And so we tried everything. We tried clouds, we tried weird atmospheric compositions, but no matter what we did, we found out the result was that the atmosphere has to be about 100 times depleted in water relative to a solar composition gas. So at some point you have to believe your data. And I was really against this because I was like, this can't possibly be right. There's water everywhere. Most models of planet formation predict a lot of accretion of icy stuff. But at the end of the day, the data say what they say. Similar results have also been found from the ground. So here's a really intriguing measurement from Pelletier et al. From last year for the hot Jupiter Tau Boo, where they also found a factor of about 100 depletion in water based on high resolution ground-based spectroscopy. But interestingly, they didn't find the same depletion for carbon monoxide. So this would be pointing to a very high carbon to oxygen ratio. So normal carbon, super depleted oxygen. So the question, I think, is whether these low atmospheric water abundances are physically realistic or not. And they may be. So here's a cartoon from some work by Aaron Schneider and Bertrand Bitsch showing how you might be able to get a very dry atmospheric composition. And the basic idea is that if you form your planet by pebble accretion out beyond the water ice line, so your water is frozen out into icy pebbles, eventually you build up your protoplanetary core by accreting pebbles. Eventually you reach what's called the pebble isolation mass, where there's a pressure bump that prevents the additional accretion of pebbles, and you only accrete the surrounding gas, which is very dry because all of the water is frozen out of the gas. So you have this very water depleted gas. And so perhaps what we're seeing is evidence for exactly this planet formation model. I think, this is all pretty speculative. Fortunately, we have much better data coming soon, in particular, extremely soon, JWST data coming. And this is a simulated JWST spectrum from the Transiting Exoplanet Early Release Science Program. So that this is actually going to be observed for a hot Jupiter. It has previously been observed with Hubble. So those are the yellow points right here. But what JWST will bring is a much higher precision because it's a bigger telescope, but also much broader wavelength coverage. And so previously we were limited to just to this water feature here. When you add JWST data, you get access to all of these different spectral features. So methane, CO, CO2, depending on the temperature of the planet, you can even get NH3. And so I think that the measurement precision and also the total chemical inventory for the planet atmospheres is going to increase dramatically in like 2 months. So I think that these observations are scheduled for July. So I think we're just like right at the threshold of really revolutionary change in our understanding, which is super exciting. I think I won't go into too much detail, but JWC is not the only big advance coming up. There's also a lot of progress being made from the ground. So one of the projects that I invested in as part of my new department is the upgrade to the gravity instrument on VLTI. This is a ground-based interferometer operating in the K-band that was originally designed to observe the orbits of stars in the galactic center, but turns out to be fantastic for exoplanets too, because with interferometry, you can just spatially separate the planet and the star without the need for a coronagraph. And this simulated spectrum here is for, I think, one of the HR 8799 planets. I have never seen an exoplanet spectrum that looked anything like that. To me, this looks like a stellar spectrum. So I think, like, I don't even want to speculate about what those data will tell us, because I think the models are so incomplete that it's, I mean, we'll see what direction the data leads us in, but that's expected for mid-2020s. Later in the decade, the ELT will see first light. And ELT will be fantastic for both direct imaging and also this high spectral resolution observations of exoplanet atmospheres, where you can actually see individual absorption lines from the planet. And so you can detect rarer species or things that are less spectrally active. You can also look at the shape of the line to learn about the atmospheric dynamics. So what is the wind speed? Maybe even like, you know, like if you're looking at a transiting planet, you see the morning terminator and the evening terminator, and those things may have different composition, different cloud properties. And by spectrally resolving the lines, you can start to distinguish where in the planet you're seeing. And in addition to all of this, later in the 2020s, we have Ariel coming online. So Ariel is a dedicated space mission that will observe spectra for a sample of 1,000 exoplanets. And I think this is also to augment the super detailed studies that James Webb and some of these other facilities will do for a small number of planets. I think that exoplanet atmospheres have shown such diversity that you really need a big sample if you have any hope of a comprehensive understanding of the atmospheres. I was asked one time by a cosmologist, he was like, Laura, like what are the 6 parameters you need to study exoplanet atmospheres? Like, when are you going to have a universal theory of planet formation? And I was interviewing, this was Cambridge, so I was like very serious, but I just had to laugh at him because I thought that question was so funny, to think that we would have 6 numbers and like planet formation would be solved. So I think Ariel will be super important. I think we'll get a great preview of the the possible range of what these atmospheres can look like, but you got to have 1,000 at least if you want any kind of systematic understanding. Okay, so this is a pretty blockbuster decade. I want to switch gears now and talk a bit more about smaller planets. And I'm calling these Earth cousins. Earth twins I'll get to at the very end. But by Earth cousin, what I mean is a planet that is a little bit bigger than the Earth, or a little bit hotter. And these are easier to study simply because the scale height of the atmosphere is higher. And so I think the prospects of getting good data for these Earth cousins is much more promising in the very near future than it is for true Earth twins. So first, I want to focus on planets a little bit bigger than Earth. I think I said earlier, I like to call these things Neptuni. So this plot is showing the famous radius gap between rocky planets and this other population of planets that we don't know exactly what they are. If you are 2 Earth radii or larger, you have to put some type of volatile envelope on your planet. So a little bit of hydrogen, but could also be extremely enhanced in water, or carbon dioxide, or methane. You can't identify uniquely what the bulk composition of these planets are based on their masses and radii alone. There's a lot of degeneracy in the interior structure. So you could have a dense core of rock and iron with a fairly light envelope on top, or you could have essentially 100% water for some of these planets. And the masses and radii would be virtually identical. So these provide a challenge and an opportunity to learn about this type of planet by studying their atmospheres. And they have proven to be extremely difficult. So the most famous or maybe infamous example is a planet called GJ 1214b. We used to call this a super Earth, but I'm changing the name to Neptune. And this planet is in many ways very representative of this overall population. It's about 2.7 times the radius of Earth, about 7 times Earth's mass. Its equilibrium temperature is a little over 500 Kelvin. And it is special only because it is the most observable of all of the planets in this population, at least in principle. But what we found after very, very intensive observations with Hubble, so 15 transit observations put together, at the time that was a record for the most intensive Hubble observation of any planet, we measured this extremely flat spectrum, completely featureless, consistent with a flat line. But the data were so precise that we were able to rule out big parts of parameter space. And so we were able to rule out high mean molecular weight compositions, even pure water, pure CO2, which would be the smallest scale height. And instead, no matter what you make your atmosphere out of, you can't make the spectrum that flat unless you put clouds or hazes in. So this is very definitive evidence for clouds and haze in the atmosphere of one of these small planets. The clouds would have to be very different from our expectations of clouds on Earth. So this figure is showing the retrieved cloud top pressure for a very simple model. No matter what the atmosphere is made out of, the cloud deck would have to sit at a pressure of roughly 1/10 of a millibar or less. For reference, Earth clouds are a couple orders of magnitude higher pressure. So these are very, very high up in the atmosphere. They would also be formed out of different materials. So at the temperatures on the planet, you would expect equilibrium condensation of salts and sulfides, so things like potassium chloride or zinc sulfide. You can also get photochemical haze formation. If there's methane in the atmosphere, it can be broken up by high energy radiation from the star and recombined into hydrocarbon hazes, or sort of photochemical soot-like things, analogous to what you've seen in Saturn's moon, Titan. Just for fun, if you take some of these cloudy and hazy models and you convolve them with the human eye response, you can answer the question, what color would the planet be? This is one of the most common questions that I get asked. And most of these colors are kind of ugly, to be honest. I once told a journalist maybe the planet was pink because I didn't know the answer. But probably it's more of a like greenish brown color. The only one of these that is definitively ruled out is this one here. And the two different rows correspond to what the planet would look like, illuminated by two different colors of stars. So if it's illuminated by the sun, you get this bottom row, but its host star is actually a small, much redder star than the sun. And so it makes the atmosphere even murkier looking. Okay. But we know that this is a really important point, that the body of spectra for planets of this size, these Neptuni, are not all as flat as GJ 1214b. In fact, GJ 1214b is shown at the very bottom of this plot. You can see how spectacularly flat the spectrum is. It really has not been matched by any other measurement since. But a lot of these planets actually do have small water features, and particularly the hotter planets. The higher the temperature is, the larger the water features are. And so I think that could point to maybe less haze happening for the higher temperatures. You really need methane to super efficiently form haze. And so if you can go just above the temperature where methane is favored, you might clear up the atmosphere and have an easier chance of learning about it. A really interesting development very recently is that one of the coolest Neptuni actually also has large spectral features. And this is a really famous case called K218b. This planet is in the habitable zone of its host star, so appropriate temperatures for liquid water to condense. And it has this gorgeous water absorption feature. So it's the familiar bump at 1.4 microns that we're always looking for. And that was kind of a surprise because we were thinking that the hotter planets would have less cloudy atmospheres, but here's one of the coldest ones we've ever looked at. And here's this really beautiful water feature. And there is some lab data that may explain what's happening. I mean, we have a sample of one planet, so it's hard to generalize too much, but what is important to take away is that I think these measurements really inspired some lab work that is super thought-provoking. And so this is a result from Xinting Yu from last year, where she measured in the lab the surface energy of haze particles. And when I read her paper, I didn't know what surface energy was, but the way you can think about it is like how sticky the particles are. And so the higher the surface energy, the easier it is for haze particles to stick to each other and clump up and condense and grow heavy. Where they can rain out of the atmosphere. But for very low surface energy, the particles don't clump up. And so you're left with small particles that are light and can linger in the upper atmosphere. And her lab work showed that there's actually a sweet spot for low surface energy right around 500 Kelvin, where GJ1214b lies, where you would actually expect those planets in sort of the 400 to 600 Kelvin range to be the absolute haziest, whereas higher temperatures and lower temperatures both would be less hazy. So I think this is really provocative. I don't know if this is right, but it is, it's noteworthy that Earth is not super hazy. And so perhaps if we start to push to these lower temperatures, even for larger planets than the Earth, we may be able to see what their atmospheres are made out of. So I think this is another area where we're going to see a lot of progress in the next couple of years. Okay. Quickly, I will talk about rocky planets. So everyone is really excited to observe rocky planets with JWST. We have had, for all of human history, a sample of only 4, well, or 5, depending on when you were counting, small rocky planets in our own solar system. And for these planets, there's a zeroth order question that is not there for gas giants, which is, do they have atmospheres at all? For bigger planets, we know from their masses and radii that they have to have some kind of envelope, but for a planet the size of Earth, we don't know. In the solar system, we have both extreme examples. So we have Earth and Venus with thick atmospheres, Mercury and Mars with virtually no atmosphere. And we also know that the solar system is not typical in an important way, which is that we have a sun-like host star for our planets, but most of the rocky planets in the solar system actually orbit smaller M-dwarf stars. And this is kind of a blessing and a curse all wrapped up into one. There's a lot of these types of systems, so small planets with small host stars. They're easier to characterize because the planets are relatively large compared to their stars, but their atmospheres might be in trouble. And the reason for that is that small stars are very bright at high energies during their youth. So M-dwarfs spend about 1 billion years where they're emitting a lot of UV and X-ray and EUV radiation that can very efficiently evaporate the atmosphere of a planet. And so it's possible to lose many Earth oceans worth of water from a rocky planet orbiting an M-dwarf. In addition to that, the planets are expected to be tidally locked all the way out to the habitable zone because they're very close to the stars. So the gravitational pull from the star holds them into this tidally locked configuration. If that's if for a tidally locked planet, you can have a permanent, your permanent day side is hot, your permanent night side is very cold. And so you can have key volatiles freezing out on the night side, leaving you with a totally dry day side and an ice sheet on the night side. Depending on which theorist you talk to, there are ways around all these problems. You can like reinflate your planet by outgassing later. If you have an ocean on the planet, that can help with circulation from the day side to the night side. So I think it's totally possible that some of them do have atmospheres, but we just don't know. Okay, so there has been a ton of observational effort to try to measure spectra for the most accessible rocky planets, particularly the TRAPPIST-1 system, which has 7 small planets orbiting a nearby ultra-cool dwarf star. And so far, all of the data have ruled out very puffy hydrogen-rich atmospheres for the planets. This is good news. We don't expect them to have those atmospheres anyway, because you have to have a super finely tuned amount of hydrogen before you puff up your planet to something that's much bigger than what is observed. But it's still totally possible to have high mean molecular weight compositions. So that would be like Earth's atmosphere, Venus's atmosphere, dominated by water, nitrogen, methane, CO2. You can also have clouds, which would shrink your spectral features, or there could be no atmosphere at all, and we just don't know. There is a shortcut that I really like to try to identify whether an atmosphere is present or not. And the idea is that rather than trying to measure a transmission spectrum, you can measure a phase curve of the planet orbiting its host star. And so as I mentioned, the planets are expected to be tidally locked. So you'd have a hot day side and a cold night side. But how hot the day side is depends a lot on the properties of the atmosphere, because what atmospheres are good at is recirculating that heat from the day side to the night side. So the idea is that if you have a thick atmosphere, the temperature difference between the hemispheres of the planet goes down. But if there's no atmosphere, you have the hottest possible day side and a night side that is effectively zero. So this idea had been thought about a lot of times. I listed some of the papers on the bottom of the slide, but only very recently was it possible to actually measure this for a known exoplanet. Unfortunately, TESS discovered LHS 3844b, my personal favorite planet at the moment, in 2019. And this is a typical small rocky planet with an M-dwarf host star. It's about 15 parsecs away. What is special about it is that it has a really short orbital period, just 11 hours. And so the equilibrium temperature of the planet is about 1,000 Kelvin. That is hot enough to measure, but not so hot that the atmosphere would have necessarily been lost. So if you put a Venus-like atmosphere on the planet, in principle, it could survive for 5 gigayears. So I got really excited about this. I wrote a really ambitious Spitzer proposal to observe 9 continuous orbits of the planet over 100 hours. This proposal was like really bold. I actually, my postdoc mentor at the time told me it was a huge mistake and they would never give me that much time, and I did not listen. And he was wrong and I was right. And this is what we measured. So this is the thermal phase curve of LHS 3844b. Just like the cartoon I showed, you can see the hot day side of the planet rotating into view. Then at orbital phase 0.5, the planet moves behind the star, so any thermal emission is blocked. And then it peaks back out, and you can see the hot day side rotating back out of view. So right away, I knew when I looked almost at the raw data, and I knew this was bad news for an atmosphere on the planet, because you can see this beautiful, very large phase modulation. And what that means is that the day side is way hotter than the night side. So we got a day side temperature of about 1,000 Kelvin. The night side is consistent with 0. The phase curve is symmetric about the substellar point. If there's atmospheric circulation, that can give you offsets in peak brightness, but that we're not seeing that. So I saw the data and I thought, all right, no atmosphere on this planet, unfortunately. we did our homework really carefully. So this is some nice modeling work from Daniel Cole and Caroline Morley, where they predicted the secondary eclipse depth, so the dayside brightness of the planet for various types of atmospheric compositions. We were considering here mainly oxygen and carbon dioxide mixtures. We found that no matter what we made the atmosphere out of, the surface pressure had to be less than 10 bars. For a pure CO2 atmosphere, we could rule out surface pressures as low as like 0.1 bar. The more CO2 you put in, the lower the surface pressure has to be, since we were observing right in a CO2 absorption band. So the data are ruling out thick atmospheres. Thin atmospheres are expected to be unstable. So it's pretty easy to erode, between 1 and 5 bars of atmosphere over the lifetime of the planet. And so we think that most likely what we're looking at is the rocky surface, which of course opens up the possibility to ask, like, what kind of rock are we looking at? And so here is our thermal emission measurement, the black cross, compared to a couple of different rocky surface models. And you can see that the surface has to be really dark. So basaltic composition fits really well. That's similar to like the black sand you would get in Hawaii or in Iceland. You get this from cooling lava, similar to the surface of Mercury or the lunar mare. And so perhaps, this is very speculative, but perhaps what we're seeing is the leftover rock from what once was a magma ocean that has now cooled off to be very dark rock. I have JWST data coming for this planet where we'll get the complete spectrum from 5 to 12 microns. So stay tuned for that. I think that'll really help start to distinguish better between these models. Okay, so just a couple more slides. I want to make sure there's some time for questions. JWST is going to be really exciting for rocky planet atmospheres. I think the first order question of how often and what temperatures do we expect atmospheres to exist for rocky planets around M dwarfs, I think we'll make huge progress in answering that question in the next couple of years. If there are atmospheres, we expect to get basic information about their composition. So here's a simulated spectrum for TRAPPIST-1b compared to different atmosphere models. These were inspired by the solar system. So Caroline Morley ran some models assuming an Earth-like atmospheric composition, a Titan-like atmosphere that would be dominated by methane, or a Venus-like atmosphere dominated by CO2. And you can see that, with data like this, you can distinguish, roughly speaking, between these different models. So I think the, oh, sorry, I have to sneeze. Okay. I think that the primary question that we'll address in the early years of James Webb is, are there atmospheres or not? And if there are, and I hope that as you start pushing to a bit cooler planets, some of them will be able to hold on to an atmosphere, we'll get a first idea of what the dominant chemical composition is. So I think this is a super exciting, very, like we're about to find out. I'm like on the edge of my seat. However, as exciting as all of this is, it is not good enough to actually get us to the question of whether the planet is inhabited. So on Earth, what we'd typically consider the smoking gun evidence that the planet is inhabited is that there's both oxygen and methane present in the atmosphere. Normally, those molecules would react with each other to form other things. And so there must be some constant source of production that's keeping the atmosphere out of chemical equilibrium. And that's the principle, the overarching principle that would show us signs of life on an exoplanet. But in order to robustly do that, we need better spectra than we're going to get with James Webb. We also want to be able to study rocky planets around sun-like stars. As I mentioned, the rocky planets with small host stars are by far the most accessible. But if you put a rocky planet around a sun-like star, you can't measure the spectrum, not with JWST, it's too hard. So the need for a next generation space mission was very widely recognized both by NASA and the European Space Agency. The top scientific recommendation for long-range planning exercises for both organizations recommended a a space telescope, either something with a coronagraph or a star shade where you can block out the light from the star and measure the spectrum of the planet directly. Or an alternative concept is being led by Sascha Klanz here in Zurich, and that would be an interferometer in space operating in the mid-infrared, where you could actually get a thermal emission spectrum from a rocky planet rather than an optical reflected light spectrum. I think there's a lot of value in exploring both ideas. So this is exciting. The path is long. The plan would be to spend the next 20 years building a mission like this, but I think the science is so exciting, we should do it. And there's going to be a lot of exciting steps along the way. So I think we have a couple of minutes left for questions. I will end there. Thank you so much for your attention.
Great. Do we have any questions?
Go for it.
I was wondering, when you simulate the spectrum,
Mm-hmm.
what is the biggest uncertainty still in these models?
Like for this one, for example, or like these ones?
Maybe in very general, like
Yeah, I think,
clouds and hazes, and I don't know.
yeah. I think the atmospheric composition itself is the biggest, like we have no clue what like redox state the atmosphere would be in, what the surface pressure is, like whether, yeah. So I think that's like 0th order, the biggest challenge. And then there's a lot of first order stuff like disequilibrium, like how much mixing is there? What is this, you know, we talked about this, like the interior exterior exchange, photochemistry, like how the atmosphere is evolving over time, so atmospheric escape and erosion, like, so it's hard to pick one. But I think these models themselves from Caroline are extremely simple. So she just said, okay, like suppose you took exactly Earth atmosphere composition and you put it at the temperature of TRAPPIST 1b and you assume like a radiative convective equilibrium TP profile, this is what you would get. And so like, we know that that's not right, but it was someplace to start. Yeah, good question.
Similar question.
Yeah, yeah, they do. It's a tough like philosophy of science question, I think, to know how much complexity is the right amount for the model, because the data, like looking at data like that, like I would be thrilled if we measured that, but also it is limited, like the signal to noise is limited, the spectral coverage is limited. And so I think it's important to run models that are more realistic and just see how much of a difference it actually makes and whether that would be something that's detectable in the data. Yeah.
Yeah, I also
Yeah.
have a related question, but maybe it's too far. So one thing is, you account for the fact that, for example, when you increase the metallicity of the atmosphere, and then do you really then include that in, you know, then the opacity that you expect? Is it like in this sense a self-consistent?
So for these, yeah, so these are, yeah, I think Caroline would know better than me, but I think she just took like line lists that are appropriate for a high mean molecular weight composition and just did the usual like radiative transfer calculation. There is some fudge factors in here, like there were a lot of opacities that were missing, like H2O broadening and things like that we just ignored for now. So it's like right-ish, I think, but not, but there, I think there's definitely room to make these models better.
Okay, and then another question is, again, related to the other questions.
Mhm.
Why are the uncertainties always symmetric? Isn't that if you change the metallicity, you
Hmm.
have a larger uncertainty in one direction than the others? Why are
The uncertainties on the,
When you show the spectra, for example, when you look
Yeah.
at the bottom, it's flat.
oh, like
or
this.
also this one here. I mean,
this
it's
one?
just they always seem symmetric. and I
So
just
this
wonder
is
why they
just,
are.
so this is just the data. Like so hold on, let me go back. Mm,
Okay, but then the data, why is it always symmetric? Why do you
so
always
it's just a brightness. So it's not like, so I think the place where you would see the asymmetry is here.
Mhm.
So like the data, so these data points are just measuring a physical size. And so there's no asymmetry there. It's like, it's totally linear. Either the planet is bigger or it's smaller. I think where you would start to see the asymmetry is if you're trying to infer the atmospheric composition, right? And so that would show up here in the inferred water abundance. But that actually looks pretty symmetric too, which is an interesting question. Right, because like if you, it's not it shouldn't be linear. Yeah, and I never thought about that before. I don't actually know. Like this is in log space, so maybe that kind of like smooths out whatever's. I don't know what this would look like in linear space. Yeah, no, it's a good question. Yeah.
So we have a question from Guillermo Mazzola. So planets are out of equilibrium. For instance, Mars once had water and now is a desert.
Mhm.
So you can observe two planets with exactly the same mass, distance, etc., but two completely different atmospheres.
Mhm.
Can you deal with the time dimension? And
Mm.
more broadly, how big do you think the data set needs to be for
Yeah.
reliable predictions, e.g. that are not revolutionized by this next set of observations?
Those are okay. Multiple questions in there. I think so. I would say in answer to the first one, it would be fantastic if we could look at the evolution of rocky exoplanet atmospheres over time. In practice, what I always say is beggars can't be choosers because there are not very many planets to pick. And so we should just like look at everything that is possible and hope that the universe has given us an experiment that allows us to explore a couple of different ages. One of the big challenges is that it's hard to find small planets around very young stars because they're more active. They're so rapidly rotating that it precludes radial velocity measurements for the stars, so we can't identify planets that way. Even for the transit observations, the stars can be really active, so it's challenging. But yeah, this is definitely something that people think about, but there's no easy answer just because we're limited in what physically is possible. The second question about how big of a sample size do we need, my answer is kind of the same. But I think it depends on something that we don't know yet, which is how common it is for the planets to have atmospheres at all. Like if you had a situation where 100% of Earth analogs looked exactly like Earth, were inhabited, had oxygen and methane in their atmospheres. If that was true 100% of the time, a sample size of 10 would get you a long way because you'd have 10 out of 10, and that's enough to start doing statistics. If the answer is 1 in 100, which may also be true, we don't know, then you need, call it, 300 planets in your sample. And unfortunately, that is bigger than is feasible even for these next generation missions. So I think that we'll be able to start carving out part of parameter space, but the answer that we get depends on what the planets actually are like, and that's something we don't know. Yeah, good question. Those are hard.
Very good. So thank you. Do we have any other questions? Yes.
Maybe it's also kind of similar. I was thinking about these hot Jupiters and how some of them have water symmetry
Mhm.
and don't.
Mm-hmm.
So are you at a point where you can have like subclasses of hot Jupiters and you can look at the correlations between other classes of the
Yeah,
star or
we're trying. And at the moment, it's hard to make sense of it. There's a lot of scatter. It seems like many of the planets are cloudy, but not all. And we haven't, yeah, a lot of people are working on this to try to figure out, like, can you predict how big of a water feature a planet will have? And we've seen a few things, like there may be some trends in temperature, but it's really messy right now. So I think something like Ariel, where we would have a really big sample of 1,000 planets, is the thing that we need to be able to answer that question correctly. Yeah. Yeah.
I was wondering about nitrogen. Nitrogen, I heard some nine vitamin or so.
Mhm. Nitrogen is really hard. So I think that the best way we'll be able to study nitrogen is actually through things like HCN, but because it's much more spectrally active. Like nitrogen is a noble gas. I think finding like excess broadening, I think that's too hard. I think that's way too hard. But I think if we had a good understanding of the photochemistry, since HCN is a common photochemical byproduct, we could work backwards from that to learn perhaps what the underlying nitrogen abundance is. That's, I think it will be hard, but that's the direction that is the most promising. Yeah.
If we have no further questions, let's thank our speaker again.
Thank you.